No CAD or CAM required. Amazing 5-axis CNC machine part manufacturing techniques. Realized with customized CNC router. How to make precision A-axis parts. Hi guys. I'm going to share with you how I make parts of my 5-axis CNC machine project, especially the A-axis, by making use of a CNC router. This video is part of the 5-axis CNC machine project that I designed to produce a 5-axis CNC machine, and its A-axis consists mainly of aluminum parts. I think it will be interesting for freaks like me who are reckless and want to do high-accuracy machining in a pool work environment with no dedicated work area. It will also be explained with easy-to-understand and crazy explanations so that non-freaks can also enjoy it. Especially, there are many problems in the use of CNC routers, which may seem convenient but are often inconvenient when I actually try to use them. So, the main topic of this video will be how I actually do it using my customized CNC router. In this video, I introduce several CNC router processing programs that I'm sharing as GIFs. If you're interested, please check the description box. I hope that through this video, you will get some ideas and inspiration for part fabrication that will be useful for your projects. First of all, it is necessary to briefly describe the main project of this channel, the 5-axis CNC machine that I built myself. This machine is the second 5-axis CNC machine I'm building. I designed a completely new concept based on the experience I learned from making the first machine. As you can see, the design is quite unique. This is because I like the insane. Because when I can do what I think is impossible, I can see a shining future ahead of me. And now, I am in the process of creating the A-axis. Don't you think this is also quite a unique design? This A-axis will be made of parts cut from an 8mm aluminum plate and will be integrated with the column by bolts. This will reinforce the column structure, which is structurally insufficient in its shape. The motor is arranged in a way that achieves miniaturization while emphasizing ease of maintenance. For the shaft bearing, I am aiming for a strong axis of rotation by using a tapered bearing with an outer diameter of 42 mm and an inner diameter of 20 mm and apply preloading pressure. 2 sets of worm gears and worm shafts are also used to completely eliminate backlash. However, I cannot be sure if these will actually work until I have tested them. Isn't it interesting that theoretically they should be able to do it, but I am not sure if they actually can or not. If I were a lucky viewer who happened to find this channel by chance, I would be so impressed by this A-axis structure and by the crazy genius of the idea that I can't help but subscribe to the channel. I am sure that I would donate a portion of my liquor money to the pool channel via the Super Thanks feature. Anyway, for the A-axis of this structure to perform as expected, 2 things are important. The first is high-accuracy parts, and the second is high-accuracy assembly. And the theme of this video is high-accuracy parts. High-precision assembly will be the topic of the next video. Here is a brief overview of what you need to know to use a CNC router. To understand the relationship between CAD, CAM, and CNC routers, let's start with the basic role of each element. Computer-aided design, CAD, is the process of creating a drawing or 3D model of a product. This allows for highly precise design. Computer-aided manufacturing, CAM, on the other hand, refers to software that automates the manufacturing process based on the design created by CAD. And a CNC router, Computer Numerical Control Router, is a machine that reads the program generated by the CAM software and physically cuts the material according to its instructions. By using CAD and CAM, the processes from design to manufacturing can be smoothly coordinated to efficiently manufacture highly complex shapes and accurate parts. For those of you who think I don't know what I'm talking about, let me explain it more clearly. For example, imagine that I am so terribly handsome that I have to make photo books for all the women in the world at their request. In order to make photo books, I need a photographer to take pictures of me. This is CAD. Next, there needs to be a person who can think of a composition based on the photos taken by the photographer and make it ready to print as photo books. This is CAM. The machine that prints the photo books is the CNC router. This process is what creates the photo books that women around the world are so passionate about. However, not all projects require advanced CAD and CAM solutions. Writing G-code directly simplifies the process and saves time, especially for simple machining. This is where the role of GRBL and CNCJS becomes important. GRBL is an open-source firmware for easy control of Arduino-based CNC machines and CNC routers. GRBL has been widely adopted because of its simplicity, but its simplicity has a major problem. Variables and functions are not available. However, by using CNCJS, this disadvantage can be overcome to some extent. That is, CNCJS macro function allows programming with variables. This allows for more flexible control by using variables to dynamically change values within the machining process. For example, one would change the size of the drilling process to a different size simply by changing that variable. Let me explain in a simple way. For example, the printing machine that prints photo books is a GRBL. If operated properly, the machine will run. The operator of the machine is the CNCJS. This is what makes the machine run. And what I want to say is that this operator is not a drunken old man, but a beautiful, smart woman who is kind of nice. And what I mean is that I can have her take my picture directly and print it. That way, I could print very quickly. This approach means that I save time without having to go through CAD and CAM. I will describe the process of machining my parts. This is a method that I devise day by day in my pool working environment. First, let me briefly explain my approach to parts fabrication. 1. Use a band saw for cutting materials as much as possible. 2. Use a hand saw for parts that cannot be cut with a band saw. 3. Use a drilling machine for small holes. 4. Use a CNC router for curved lines, large holes, and holes that require accuracy. The first 3 need no particular explanation, because you can see them when you watch the video. The point of this video is to make machine parts efficiently using CNCJS variable functions. Maybe if you have actually made mechanical parts before, you will understand what I'm talking about. So let's start making the parts. First, cut the large plate with a band saw. The parts that the bearings will fit into our machine first with CNC for their holes before the parts are cut out. Otherwise, there will be no place to clamp the part and machining may become difficult. You may be mesmerized by my athletic and beautiful legs, but look more closely at the work situation. Something is wrong. It made some strange noises and stopped working. A problem has arisen. The belt on my favorite bandsaw broke. I never thought that the belt on my bandsaw would break. I had not prepared a spare belt, so I had to think of a way to deal with the problem. I had no choice but to first cut the material with a hand saw and then machine it with a CNC. Even with my well-trained body, this job is incredibly tiring. I usually use a bandsaw to do as much work as possible and cut what I can't with a hand saw. I also have a jigsaw, but I don't like to use it because it is too loud. Arc machining is difficult to do by hand, so I use a CNC router. In this case, there is an advantage to manually entering the G-code. The process of generating G-code using CAD and CAM remains the same, even for the simplest of machining. Therefore, for operations such as arc machining, it is faster to enter the G-code directly. You might think that you can just machine everything with CNC, and you would be right. I already have a 3D model in CAD, so if I had a CNC machine that could set up all the material, I would do so. However, this small Q-tread machine I have does not have that much stroke. To machine a large part, I have to split up the machining process by moving the part around several times. Especially now that my bandsaw has broken down, I need to do a lot of machining on the Red machine, and with CAD and CAM, this is a lot of work. That's why I need direct input of G-code. Earlier I talked about the validity of entering G-code manually, but there are some practical problems that also exist. If one simply wants to perform a circular arc machining operation, the task is quite simple. In practice, however, few machining operations are completed in a single cut. For example, it is common to machine an 8 mm aluminum plate in 4 separate cuts of 2 mm each. In this way, not only the arc to be machined, but also the process of lifting the Z-axis to a position where it does not interfere with the part after machining is complete and returning it to the starting point of machining must all be instructed in G-code. As a result, machining that is often thought of as simple actually becomes a complex process. One way to solve this problem is G-code, which makes use of variables and functions. For a particular machining pattern, the program can be easily modified by simply changing the value of a variable. It's getting a little difficult, so I'll try and make it easier to understand. For example, let's create a program to process a square. The length of each side is the same, so if I want to change the size of the square, I need to change 4 numbers. However, if I have to make a lot of changes to change the size, it will be too much work and I will lose my mind. That is why I set the length of each side as a variable, so that changing one of the variables can easily change the size of the square. However, there is another problem here. GRBL, the CNC control program, does not support variables or functions. To solve this problem, I use a macro function of CNCJS. This is the CNCJS control screen. I think the interface is very intuitive and easy to understand. And here are the main functions I'll be using this time. With this macro function, I can use the variables I just described. Furthermore, I found that conditional branching can also be used, and that it can be used like a conditional branching function. Furthermore, since it seems to be able to use JavaScript, I think it is possible to create quite complex programs. However, I have genius ideas and good looks, but I am very weak about programming, and I know only the name of JavaScript, so I will not use JavaScript this time. In the machining of plates, it is common to perform several continuous straight-line machining operations. This time, I would like to introduce a program that I actually created and found useful. I created a program that automatically performs the same movement 3 times by specifying the XY coordinates of the endpoint of each straight line. This program was very useful for me because the machine is small and I need to machine parts by changing their positions many times. The holes making program is very often used. In fact, this program may be the most commonly used. In the holes making program, it was necessary to change the number of times to make a hole depending on the size and depth of the hole. It seems that with JavaScript I can create a conditional branch that cancels part of the program, which is usually impossible with GRBL alone. However, being the genius that I am, I came up with a good idea. It turns out that when GRBL finds an error in the G-code, it skips that line. Using this, I can now create sequence numbers that cause errors in conditional branches and cancel lines that I don't need. The hole size can be freely determined by simply specifying the hole size, depth, and number of machining cycles. There are several advantages of this hole drilling program. 1. It can make large holes that I cannot drill with my drill machine. This worm wheel needs to make large hole. Even such a large hole can be easily machined by simply changing the variable. Two, I can make accurate holes. The hole where the bearing fits needs to be accurately holes. Especially for the holes to fit the tapered bearings, I want to press fit the bearing outer rings to eliminate the gap, so I measure the dimensions and widen the holes little by little. Setting the number of machining cycles to 0 executes only the finishing process. Measure the inside diameter of the hole and enlarge the hole a little at a time until it is the size I'm aiming for. This is best done by direct G code input. Three, the distance between the holes is accurate because the hole center position can be specified. The distance between the bearing holes of two worm shafts can also be machined accurately. All of these programs are all in one program and can be machined by simply changing variables. The processing center can be specified here. If I change only this point, it can be precisely and accurately positioned as required. Of course, these holes are also adjusted so that the bearing will fit in just the right place. This kind of processing is very important when making machine parts. All of these programs are all in one program and can be machined by simply changing variables. Let me introduce you to a wonderful program that I have created. This program can move a rectangle and can specify the radius of the four corners. As a result, it can machine slots in both the X and Y directions. This is very useful when making stepper motor brackets. This motor bracket features a large hole in the center, surrounded by smaller holes for attaching M3 bolts, and further out, holes with slot machining. These operations are performed using a single program with variable adjustments. Please watch closely. The sequence number represents the number of processing steps. Once the specified number of steps is exceeded, the sequence number is intentionally set to a negative value to trigger an error and cancel that step. Sequence number 9999 is designated for the final finishing process. By changing the program's variables, you can easily create the program for drilling the next hole. We'll continue to adjust the specified variables in this manner, Simply changing the coordinates allows you to create the same slot at a different location. In reality, while I'm working on a project, I check the 3D model's blueprint like this to identify the location for the next hole and update the program accordingly. As soon as the current program finishes processing, I can immediately start on the next task, allowing for almost continuous operation. How about it? Are you starting to get the hang of it? By utilizing variables and G-code like this, you can easily change dimensions on the fly without relying on CAD and CAM, simply by observing the machining process. There's no need for intricate, high-precision work on this bracket. However, as mentioned before, even when dealing with strict dimensions like the holes for bearings, adjustments are straightforward. Using CAD and CAM would require constant revisions to the drawings, generating G-code with CAM, sending it to CNC and then machining again. Finishing operations are the same. Creating a dedicated program and changing its dimensions can be quite troublesome. But by using variables and G-code, all these tasks can be easily accomplished. That's it for the CNC machining. Since the new bandsaw blade has arrived, the next step is to cut the parts with the bandsaw using this new blade. This roughly outlines my method for machining parts. While CNC machining offers considerable convenience, it can become cumbersome when making just one part. This is especially true for DIY part production, which often involves making individual pieces. Using CAM for all machining processes can be highly inefficient in these cases. Therefore, for non-mass-produced items, I believe it's more efficient to use CNC partially and complement it with manual tasks. How about that? This concludes the content for now. It might have been quite niche, but did you enjoy it? Longtime viewers of this channel might have noticed, but I believe there's a different feel to this video compared to our previous ones. I'm convinced that the recent developments in AI technology are revolutionary and extremely important in fulfilling our viewers' desires. The major challenges for this channel involve increasing our video posting frequency, creating more entertaining content, and most importantly, securing the time to advance our DIY projects. I think utilizing AI effectively could allow us to achieve unimaginable results. Whether you view this video as an evolution or a regression is up to you, but I hope you'll at least recognize us as a unique channel unlike any other. What the future holds is uncertain, but I have no intention of becoming just another run-of-the-mill YouTube channel. If you are interested in this project, I suggest you subscribe to my channel so you don't miss any videos. If you empathize with my project, why don't you become a member and support this channel? There are a few benefits, but as long as you are a member, your name will appear at the end of the videos as a patron. In other words, you can be a part of this project. So, please look forward to the next video.